In this video, we're going to continue with our discussion of continuous functions. So recall that if we want to find the limit of a function, and we know at some value x equals c, and we know that the function is continuous at c, then we can just plug in c into our function. So just evaluate the function at that value c, and that will tell us what the limit is. So that's a really nice property to have. So let's go ahead and point out some functions that are continuous everywhere in their domain. Right? This will give us a big list of functions that we can work with as far as limits go. So the following functions are continuous at every number in their domains. All right. Well, we've already said that polynomials are continuous. That was actually back in section 2.2 that we saw that. So when we first discussed limits, we saw that polynomials were continuous because to find the limit as x approaches c of some polynomial, all you had to do was plug in c into that polynomial to find out what that limit was. All you had to do was evaluate the function. Same was true for rational functions. Right? So a polynomial over a polynomial, as long as that denominator was not 0, then your function was continuous there. And again, we're saying here continuous at every number in their domains. So when the rational function is 0 in the denominator, then that point is not in your domain of that rational function. So these two are continuous everywhere in their domain. So are root functions. So are trigonometric functions. So are inverse trig functions, which we're not going to talk about in this class, but you'll do more in Cal 2. Same for exponential and logarithmic functions. You'll see these in Cal 2, but we can go ahead and point out that these will also be continuous functions on their domain. Those functions are continuous on their domain. Everywhere, at every point on their domain. Okay. Well, how about we look at an example here? Let's show that the piecewise function f of x is equal to sine of x if x is less than pi over 4, and cosine of x if x is equal or greater than pi over 4. Show this is continuous on the interval negative infinity to infinity. Oops, there we go. I want to show that that is continuous on everywhere. It's continuous from negative infinity to infinity. So the first thing is note that both sine of x and cosine of x are continuous on their domain, which their domain is the entire real line, so from negative infinity to positive infinity. So f of x is continuous on, well, sine of x is, f of x is defined by the function sine of x when x is less than pi over 4. So f of x is defined, and continuous from negative infinity to positive pi over 4. And f of x is continuous on, and now since f of x is cosine of x from pi over 4 onward, then we are continuous from pi over 4 to infinity. Since cosine of x is continuous everywhere, and in particular on this interval. So we get that both of these intervals, for both of those intervals, f of x is continuous on those entire intervals. So our only issue really is what happens at x equals pi over 4. Well, we need to find the limit as x approaches pi over 4 from the left of f of x. Well, this is the limit as x approaches pi over 4 from the left of, well, our function f of x was defined to be sine of x when it's just to the left of pi over 4. So this is really just the limit as x approaches pi over 4 from the left of sine of x. And what is that? Well, sine of x is a continuous function, so to find this limit, we could just plug in pi over 4. So this is sine of pi over 4, which is root 2 over 2. Okay, now let's find what the limit as x approaches pi over 4 from the right of f of x is. Well, to the right of pi over 4, f of x is defined by the function cosine of x. Cosine of x is continuous everywhere, and in particular at pi over 4, so we can just plug in pi over 4 here. But what is cosine of pi over 4? That is root 2 over 2. So these two limits exist, and they in fact equal each other. So if they equal each other, this tells us that the limit as x approaches pi over 4 of f of x is in fact root 2 over 2. So this limit exists, and it is root 2 over 2. Then what do we need? We need to know what the function value at pi over 4 is. What is that? Well, this is, by our definition of the function value here, that is cosine of x when x is pi over 4. So this is cosine of the x value. Our x value is pi over 4 here. That is root 2 over 2. So our limit exists. It is root 2 over 2. Our function value exists. It is root 2 over 2. If we put those two things together and they are equal to each other, so if our function value equals our limit at that point, then our function is continuous there. So f of x is continuous at x equals pi over 4. All right. So, as we said earlier, the function is continuous on the interval, open interval from negative infinity to positive pi over 4. It's continuous from positive pi over 4 to infinity. And now we've also shown it is continuous specifically at the point x equals pi over 4. So we're done, right? The function is continuous everywhere on this interval. So everywhere on the real line. All right. That concludes that example, but there is some more stuff we want to cover in this video. In particular, that is two quick statements here. Theorem is that if f is continuous at c, and if g is continuous at f of c, then the composite function g compose f is continuous at c. All right. So for composite functions, if the original function f is continuous at c, at some x equals c, and then whatever our output of that is, if g is continuous at whatever that output is, then the composite function is continuous at c. Okay. And then there is one last thing we want to talk about, and so I'm going to write out a theorem, and then from there we'll look at a picture to see what that means. So theorem, the intermediate value theorem. if f is a continuous function on a closed interval a to b, and if y naught is any value between f of a and f of b, then y naught is equal to f of c for some c in the open interval a to b. All right, now what does this all mean picture-wise? Let's draw a picture here. We have some function here that is continuous between x equals a and x equals b. So we have some y value f of a here, and we have some y value f of b here. What the intermediate value theorem says is that if we select any horizontal line here, y naught, there is some c, at least one, maybe multiple, but some c value, so x equals c, between a and b, that f of c is equal to y naught. So we evaluate our function at that point, and we get y naught. That's all that intermediate value theorem means. Now, to get a better idea of the power of that and really what all this means, let's suppose our function is not continuous. So how could this fail? Well, the theorem doesn't fail, but if we relax the condition and f is no longer continuous, then notice that this doesn't hold up, right? Maybe we have a function that looks like this. Here is a, x equals a, here is x equals b, and we have f of b here and f of a here. Well, what if we draw a line here? Does our function meet this line at any point? No, it does not. And why did that end up failing? And why did we not have to cross this line? Well, because our function was discontinuous on this interval, right? There was some point that the function was discontinuous within that interval. But again, if it was continuous, that means informally I couldn't pick up my pen to draw the graph. So to get up to this point, I would have had to have crossed this line somewhere. No matter what I do, I would have eventually had to cross the line if this had been continuous. All right? And so that will end our video for today.